Hey guys, welcome back to the channel. Today we're going to be finishing off the video from last time by actually looking at the last 3 concepts of integration that we need to know for the Pure 11 paper. Obviously this isn't going to be a super in-depth video as I can only cover so much, but you should be able to get a general understanding of the key concepts. To start off, we'll be going through a very quick summary of finding the area under the curve. And it's a quick summary because I've basically covered most of that in my previous video. So if you haven't seen that already, make sure to click the link below. From there, we're going to be looking at what happens when we find the volume of the curve, which is quite an interesting part. And lastly, after that, we'll be going through what to do when we're asked to integrate up to infinity by looking at improper integrals. So we touched briefly on the area of an integral before, but the question part now is, what happens when we have 2 curves? We can't really find the area the way we usually did. So what do we do here? What we need to do is first find the intersection points, okay? 2, identify which curve is on top. And from there we can integrate by basically doing the integration of the top curve minus the bottom curve. And that allows us to effectively solve that problem. This logic works for both the area between 2 curves and the area between a line and a curve. But they just look a little bit different. And that's why I've done 2 illustrations here. Just as a quick one, guys, if you're struggling to figure out what to study, how to study, and how to go through things in a bit more detail, make sure to click the link below. We have recently developed a completely free, at least for now, community where you can interact with other students, and we'll be uploading more in-depth content on there to really help you take more actionable steps. But it's completely free for now, so make sure to click the link below. Okay, so let's say we're given an example that says to find the area between the curve y equals x squared plus 1 and the line y equals 3x between the points of intersection. Okay, we first solve then x squared plus 1 is equal to 3x, and from that we find that the upper bound is 3 plus root 5 over 2, and the lower bound is 3 minus root 5 over 2. Perfect. Now, what about the top minus bottom bit? Well, our top function here is y equals 3x. Our bottom function is y equals x squared plus 1. So therefore, our curve altogether becomes 3x minus x squared minus 1. As a result, when we integrate the equation here to find the area, we therefore get 3 over 2x squared minus x cubed over 3 minus x, which is bounded between our 2 intersection points. As a result, our final area is going to be 5 root 5 over 6 units squared. Alright guys, so now we have a situation where we're asked to find the area in terms of y. Now this is an interesting one because now everything is rotated 90 degrees. And as a result, it adds a little spanner in the works, so to speak, where to find the area, we have to use y values instead of x values, per se. Alright guys, so to take an example here, let's say we're asked to find the area of the region between x equals y squared plus 1 and the vertical line x equals 5. Okay, and that's going to be between -2 and 2 on the y-axis. Okay, now for a fixed value of y, the horizontal width here is 5 minus y squared plus 1. Okay, and that gives us 4 minus y squared. So that's our new graph to integrate. And when we integrate that with respect to y, what do we get? Well, naturally, we get 4y minus y cubed over 3 between 2 and negative 2 for y values. And that as a result gives us 32 over 3 units squared. Alright guys, so now what if we move away from area and we start to go towards volume? How does that look? What does that look like? Well, let's say we rotate a 2D region around an axis. And what happens to our rectangles here? Well, our rectangles here now become circular discs. And as a result, for rotation around the x-axis, our radius becomes f of x. Our area becomes pi times f of x squared. Why? Why is that? Because of pi r squared. Our thickness becomes dx. Our volume becomes pi times the integral between the bounds f of x squared dx. And as a result, we're able to find the volume here. Alright guys, so now we're given an example where it says to find the volume generated when the region under y equals root x is rotated from x equals 1 to x equals 4 about the x-axis. What do we do here? What's the play? So what you actually need to do here is simply just apply the equation. So doing this, we get v is equal to pi times the integral between x equals 1 and x equals 4 of root x squared dx. And once we follow the patterns here, we get pi times x squared over 2 between 1 and 4, which finally gives us an answer of 15 pi over 2 units cubed. Now, what happens when we're told to integrate all the way to infinity? What happens then? Well, we obviously can't simply plug in infinity. That wouldn't make any sense. So what do? Well, there's a lot more maths that goes into this. But for purely the AS level syllabus, what you need to realize is that we can treat infinity like a moving boundary. Because what we can say is that the integral between infinity and a of f of x dx is going to equal the limit as t approaches infinity of the boundary between a and t of f of x dx. So in essence, t is tending towards infinity, and we never get to the exact area, but we get close enough. This brings us now to the concept of convergence versus divergence. Okay, I think the best way to explain this is through an example. So let's take two integrals. Okay, the integral of 1 to infinity of 1 over x squared dx, and the integral of 1 to infinity of 1 over x dx. Okay, now when we plot this on a curve, as you can see, we get two very different situations. 1 over x squared dx, or shall I say the integral of 1 to infinity of 1 over x squared dx, converges to a very definite point, that is 1. It never quite reaches it, because remember this is a improper integral, but it converges to a said point, 1. Meanwhile, 1 over x, the integral of 1 to infinity of 1 over x dx, this diverges. It never converges. It never goes towards a definite point. And as a result, the integral of that is just going to be infinity. Okay, so now to take an example of this, we're told to determine whether the integral from 2 to infinity of 1 over x squared converges or diverges. Okay, so Let's start by drawing the graph of 1 over x squared, and this provides a bit of a hint if you look at the way the graph operates. Okay. If we then go to the integral, we can say that the integral between 2 and infinity of x to the negative 2 dx is equal to the limit as t approaches infinity of the integral of 2 to t of x to the negative 2 dx. Okay, cool. And as a result, this gives us the limit as t approaches infinity of negative 1 over t plus a half. Okay, well, what do we do here? What does this mean? Well, as t approaches infinity, what happens? In this scenario, negative 1 over t is simply going to approach 0, because 1 over infinity inevitably is 0. As the denominator gets bigger and bigger, you tend towards 0. So as a result, we're simply left with a half. And consequently, our integral clearly is convergent in this case.